Okay, let's get started. I love seeing all the collaboration as people share their thought processes on the homework problems. You can tell what you've assigned is difficult when there's this much chatter ahead of a class on the day an assignment is due. All right, same announcements we had for a while. Assignment due tonight. We are going to, this is the last day of content until next Monday. We're going to have a review session tomorrow and an exam on Friday. For those review sessions, I very much like to get those recordings up as soon as possible. So usually when I go back to my office, I tell people to wait until I've uploaded that lecture video just to make sure that it happens. So if for some reason you can't make it in tomorrow, don't worry about it. There will be a recording up. That said, obviously it's better to be here than not be here, so you can make sure that your questions get addressed. Otherwise, you're at the whim of what everyone else comes up with for their questions, which sometimes are useful to you and sometimes they're not. So be here to advocate for yourself if you can. Questions about anything before we dive into more context-free? Yeah.
The hackathon, I will only make it for a little bit in the morning. Would it still be beneficial to show up for a couple hours in the morning?
That's tough. You're gonna need to have a team.
Well, just to witness, not to.
Oh, yeah, just to show up and check it out.
Yep.
Well,
You see benefit in it.
you can certainly get a sense of what the projects are just by walking around and talking to people. Hey, what are you working on? People would be happy to talk to you about that. Yeah. The best networking part's gonna be at the end where the judges are there and ready to talk about the projects. I don't know exactly what the judges' schedules are like on that day, but I would say if you have the spare time, sure, but I don't think it is the most important networking opportunity of the quarter, probably. We'd still love to see you.
With regular expressions, you write some character to the end of like an actual number.
Yeah, it does mean repeat that
is
exactly
valid.
constant number of times. Yeah. So there are a couple points in the homework where you're gonna do something like a 0 + 1, but you don't want to star it. You want to do it at some 5 or more times, 6 or more times, something like that. You can write a constant exponent to say repeat this a constant number of times. And that does work to prevent you from writing out 0 or 1 star, 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 or 0 or 1, 0 or 1, 0 or 1, 0 or 1, however many times you need it. Just write an exponent. It'll make your life a little bit easier. Anything else? All right, last time we introduced a context-free grammar and we found that we were able to derive a language that represented mathematical parentheses or coding curly braces, and that was really cool, that a very simple grammar could represent scope. So we're going to get into what I hinted at the end of yesterday's class, which was a difficult question to ask about this and to answer is something like, now I have this program. I'll strip out everything except the curly braces. Is the curly braces a sentence in this grammar's language? So we need some way of being able to parse this grammar and say, can we generate this string, yes or no? Unfortunately, based on the length of that, you can imagine that this is exponential in complexity. You're gonna pick ASB or SS or lambda, so you have a branching factor of 3. You have 3 to the power of the length of the number of curly braces you have possibilities to generate. And you're gonna have to go through a deterministic breadth first search or depth first search to try to generate and say, based on the length of that, can we actually generate this particular sequence of curly braces or this particular sequence of parentheses? That's not efficient at all. It's not going to scale to programs that have really reasonably long length, that have a lot of curly braces. So let's talk about this really interesting concept of, we'll start with ambiguous grammars, because ambiguous grammars are a problem. We'll define it to say that a grammar is ambiguous if we can produce some string, it only has to be one string in the language, by following two different paths through the productions of a grammar. Let's give you an example just so that is clearer. So here is a grammar. And if we wanted to produce the string AAB, first come up with a path through the grammar that produces the string AAB. And then once you do that, see if you can find another one. What I mean by that is we should start with something like continue this process, see if you can come up with one, see if you can come up with another one. But yeah, that's the path through the grammar that you're going to take. Starting with the start non-terminal, just continue to evaluate non-terminals, replace them with the right-hand sides until the end result is the string AAB. Note that we're looking not for the same set of productions, but the order matters for those productions as well.
Oh.
You have two different paths. Yeah,
Would it be like either starting with the A or B?
yeah, so we could lambda this A and get AAB, and then from AAB, we want to produce the B and then lambda the B. So we'll say AA, the capital B comes before the B, and then we lambda the B and get AAB. That would be one path. And you can think of this by numbering these productions. So let's say this is the first transition, this is the second transition, this is the third transition, this is the fourth transition, this is the fifth transition. A grammar is ambiguous, even if you use the exact same definitions, if you can change up the order and arrive at the same result. So I basically have these to show. I think that makes more sense to do. So here is the two different, or at least two different, there may be more of them. I think these are the only two though, that produce AAB. We can start with the same, but you can see that eventually we turned this B into BB. But if you start there, kind of starting from the right, generate the B and then generate the A's, and then lambda the non-terminals out, that's a different path through this grammar. Intuitively, why are ambiguous grammars a problem? Does anyone have a sense of why producing a grammar that allows for something like this, why would that be a problem? Yeah. Yeah.
It would be complicated to write an NFA or a DFA for it if it's regular.
Sure. Complicated to write an NFA or a DFA. I could see that.
Maybe it's not regular because of that.
Sure, not regular. This is not regular to begin with, even with the AB, yeah.
The actual, if you were to write a parsing program, it would be super hard to make, like, know what state you're in exactly.
Yeah, so if you allow for this, either optimizations or how we generate the process of this, if you are parsing something and trying to figure out, is this program in this language, we want to have exactly one way to do that. We don't want to be able to build that in different ways, because one of those ways might be more efficient, one of those ways might be, there's a problem with this concept. We'll explore that in a little bit more detail as we get deeper into and start actually talking about compilers. But in the meantime, we can at least start with an ambiguous grammar and eliminate the ambiguity if we force a particular order of non-terminal replacement. So we say, given that we're at a particular point in this derivation, we're going to evaluate the leftmost non-terminal at all points in time, or the rightmost non-terminal at all points in time. So those are called leftmost or rightmost derivations. A leftmost is going to say we're always going to evaluate the leftmost non-terminal before we evaluate anything else in the string. Rightmost would just be the rightmost non-terminal instead. And if you have an ambiguous grammar, then you can interpret statements differently, which is a huge problem for a programming language, where a particular statement needs to mean one and only one thing. So we'll come back to this and we'll justify why this is a terrible thing in terms of inventing programming languages and being able to turn programming languages into executable code. Questions on this concept for now? We're gonna continue, but just making sure that this is all clear. All right, let's look at another grammar. First kind of problem you might see related to this is something like provide both a leftmost and a rightmost derivation for a particular string. So this would assert that this string can be produced by this grammar, but there should only be one path through this grammar if we assume a leftmost derivation. There should only be one path through this grammar if we assume a rightmost derivation. See if you can come up with those derivations. That's my top of the head leftmost derivation. So we're always taking the leftmost non-terminal and replacing it. So we first need to, before we can evaluate this capital B, we need to evaluate the capital A. There's only one thing that capital A can become, so we do it. For this B, we kind of have two options now. Either this B can become the last two B's, or this B can become the last two B's. It doesn't matter which one of those you take. You just need to make a decision about the leftmost non-terminal before you make a decision about the rightmost non-terminal. Yeah.
Does it matter if you put that, the non-terminal B at the end in front of the first terminal B? In the second,
Here.
yeah,
Yes, because this capital A becomes B capital B. So this needs to be replaced with exactly that definition for it. Yeah, great question.
you just are,
Any other questions on a leftmost derivation? What can we do for a rightmost derivation? Right to left. So we start exactly the same. We have to replace S with the one thing S can be. But now we have to start evaluating these non-terminals right to left instead of left to right. So we need to replace this B with something. We can note if we're analyzing this in some capacity, we don't have enough lowercase b's yet. So we should probably make some. But each A needs to produce at least two B's. So this needs to produce at least two B's. So this can become an A at most once before we need to do that. So let's make this become an A, so we can have A, capital A, capital A. We'll evaluate the rightmost A as, now we're gonna replace this A with a definition B, capital B, B. Now we need to evaluate the B. Since we have two B's and something that's gonna become at least two B's, we need to get rid of this B. So the only thing that we could reasonably do is get rid of it. Replace it with lambda. So from here, we're gonna evaluate the A, turn that into two B's. So we have A, B, capital B, 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 and now we can lambda this B and get A, B, B, B. And we always focused on the rightmost non-terminal to get there. But note that there are still paths. We still could have, at least in the leftmost derivation, we had to make sure that, in fact, there were options in both of these. When we replaced this A and we lambdaed this B, we made it come back to an A. We could have lambdaed here and turned this B into an A to produce the last ones, rather than lambdating it once we got there. So there is a branching factor, which means this is still ambiguous, even with the leftmost and rightmost derivation. That doesn't mean there's necessarily a single path through it, but there will be fewer paths through it, which is better for searching. We'll see if I got exactly what I said. Yes, yes.
The B, oh, it just became a, oh, that's what happened.
Oh, it didn't.
Oh, wait, so
It left it to be first.
Yeah, that's fine. But it leads to a slightly different process, even though the end result was exactly the same. So there's still some ambiguity. If you were asked something like this, any path that gets you there through the grammar using the productions would be correct. As long as you're, if it's leftmost evaluating non-terminals from left to right, rightmost evaluating non-terminals from right to left. I'm hoping that I have actually introduced this concept a little early when we talked about this, but we can show derivations like this via parse trees and not just via sequences of productions applied via arrows. So you can imagine making a parse tree kind of like this, where we say if there's A arrow A, capital B, C, you now have arrows to each one of those symbols. Terminals are going to become leaves and non-terminals are going to be internal nodes that need to be evaluated or replaced with some right-hand side of a legal production in the grammar. But now you can start to envision it as a tree. We can continue to expand non-terminals, they're going to be internal nodes. All of the leaves in this tree structure will be terminals. And that way you could read the string that this produces via a depth first search of that tree. So let's give you an example of that. Let's use this grammar. Let's construct a parse tree for A, B, 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 B. So you're going to start with a single root node that is S. That's going to have 3 children. The leftmost child is going to be the terminal A. The middle child is going to be the non-terminal capital A, and the rightmost child will be the non-terminal capital B. Same grammar, same string, just now thinking about this process through envisioning it like it's a tree. And since we've mostly already gone through this, I don't think you can basically just copy what I have here as an example derivation. We can see that we apply S into a capital A B like we do according to the production that's right there. Then we need to evaluate the A and the B such that once this is all done, if you were to take a depth first search through this, we would see A, B, 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 which is the string that we were trying to derive, doing a depth first search. What's nice is you can visually see which productions were used in a particular derivation, whereas if we're just writing it out, someone still has to go back and refer to the grammar to figure out what production was used here in order to get to that point. It's kind of nice and visual as long as you can intuitively look at this and read it in depth first form. Sometimes that takes a little bit of practice to say, what is that? You're just going through the leaves from left to right. If we are parsing this recursively from left to right, then you have done a leftmost derivation. If when you constructed this, you recursed from right to left, you have a rightmost derivation. Note, though, that this is not the only tree that you could build to produce this string. And we'll talk about that in a moment, how if you have an ambiguous grammar, then you can generate multiple parse trees, multiple valid parse trees for the same string. That's still that same problem. So with grammars, we want to answer the membership question, and it ends up being a lot of what we're going to cover. And in fact, it's both of your programming projects for the course deal with this membership problem and being able to represent things more efficiently than this brute force method that I'm about to describe. So given that we have a string like A, B, 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 B in the last example, we want to answer, is this a sentence in the language that this grammar represents? To do so, if we wanted to brute force this, we could say, all right, we're going to use leftmost derivations and we're just going to generate all of them. We're just going to start generating leftmost derivations until we generate a leftmost derivation that matches the query string. So we just start looking at all possible derivations from the start non-terminal within a single step. Does it match the query? If yes, great, we found it. If no, Then we're going to backtrack. And we're going to now look at everything that we could get from one step of all possible leftmost derivations from that first step, and that's a two-step leftmost derivation. If you've taken an AI course or anything that has to do with searching algorithms, this might remind you of iterative deepening. The concept of it's a depth first search, but you're going to do a depth first search of depth 1, then a depth first search of depth 2, then a depth first search of depth 3. If you have an infinite recursed searching space, then that's what you need to do to validate or make sure that you're finding the shallowest solution. If you do a breadth first search, then you need to store an exponential amount of memory as you do this forever. Iterative deepening allows you to store the linear amount of memory that you get from a depth first search as you do this process, but now you're still getting that breadth first search result of the shallowest solution, which is good.
Does the school have any like AI classes or something like that?
Yes, yeah, you want to take machine learning, and there's a new degree being put forth, which is AI for cyber. And a lot of that is going to have some overlap with just general AI principles. I'm going to be teaching a couple of those courses, which I'm really excited about. But my game dev 2 also goes and dives a bit into AI. Because it's very important to be able to make game agents and intelligent agents within a game setting. How do you create an AI that's challenging but beatable? How do you have an AI that learns from the player's actions and tries to provide a constant challenge based on the knowledge of how that player is playing the game? So then step 3, we reject any derivations that cannot produce the query from that point. So if we're trying to produce ABBBB and the derivation that we have so far is AA, we can reject every derivation from there because we've already, since we're doing a leftmost derivation, any non-terminal after that cannot insert between those two A's. That allows us to start thinking about left to right. We can start pruning this tree that we are creating, this infinite tree that we're creating, prune branches that cannot possibly produce the query string from any children of that node. Then we're just going to loop this process, the next resulting leftmost derivation, next resulting leftmost derivation until you generate it. We can prove that if this string is a sentence in the language, then we can do this in a finite number of steps. We will have a leftmost derivation for this string in a finite number of steps. However, it's very brute force and takes an exponential amount of time, which, as we know as computer scientists, we never have an exponential amount of time for any scalable problem. We just don't. Unless one of you invents something that allows us to live forever, prevents the Earth from being engulfed by the sun, I have high hopes for you. Please do it before I die. I'm stuck lecturing about compilers for the rest of my career. I'm not going to have the chance to go do exciting things like extend my life forever. Please do it. Make it affordable too. It'd be great. Make it so a professor or teacher's salary can do it. I'm not selfish when I say that. So issues, it's really tedious, it's incredibly inefficient, and there's a really big issue we have not talked about yet. Can anyone identify what that really big issue is? Don't have huge expectations you'll see it, but maybe someone does. Beyond the fact that it's tedious and inefficient. Yeah.
If it doesn't work, you're just gonna be running infinitely.
Yes, that's exactly it. If the query string is not in the language, then there is no leftmost derivation in this grammar that will ever match it. So this process will continue to run forever without ever telling us. We will never know whether this grammar can generate that string, yes or no. We just know we haven't found it yet. So it can run forever if the string is not in the language. Because we allow the fact that a non-terminal can become lambda, we never actually can show or prove that we've reached a string that is so long that it is longer than something that could generate the query string. Even if the current string of terminals and non-terminals is 20,000 characters long, if almost all of them are non-terminals, maybe they could reduce down into a 4-character solution by just lambdaing a bunch of them. And hey, we found the one path that leads there. So we would never know yes or no. So we can answer yes in a finite amount of time. We can't ever answer no algorithmically. We'd have to have some other logic or proof that allowed us to conclude that. And that adds a very big complexity layer to this problem. We'll actually study that entire concept later on. All sorts of algorithms where we can answer yes, but we can't answer no. That is a very interesting class of algorithms that deserves a lot more time and energy and effort, and we'll spend some time on that later in this course. For now, it just produces a big headache that we need to find a way to work around. So if we don't allow lambda, then maybe we can answer no in a finite amount of time. So we cannot have a non-terminal to lambda, and we cannot allow a non-terminal to non-terminal. We showed earlier, or at least I asserted earlier, that these are useless productions. Any A arrow B, that just says that you can backtrack any definition for B back into A. But these are two kinds of rules that, while they're legal and can produce a grammar that leads to a context-free language, they introduce the issues of trying to parse this in a finite amount of time. The answer could just spin forever. Luckily, we don't need either of them. And removing either of these non-terminal or these production types does not restrict us past context-free languages. But to do so, we are going to need to have some kind of way of constructing grammars that leads to something that is more intuitive. So we're going to look at some ways to construct types of grammars that are meant to be parsed. Rather than having a grammar with arbitrary rules, we're going to restrict the rules without restricting the level of language class that we are allowed to represent, so that we can more easily write some kind of algorithm that can parse them. If we know that those productions are going to be in a couple of different rule types, then that allows us to, when we see a particular rule, branch without having that same very large branching factor. In fact, we can show that the number of leftmost derivations have to be less than or equal to twice the length of the string if we disallow those rules, which allows the concept of a leftmost derivation to terminate. Questions on that? That was kind of a dry slide, but hopefully that concept makes sense. Feel free to raise your hand and ask a question if not. Goal is to be able to terminate within some finite number of steps, answering yes or no. This grammar can produce this string, or this grammar cannot produce this string. Right. Complexity of brute force parse. I've already revealed that. Every leftmost derivation, we multiply the current number of potential derivations by the number of productions in the grammar, because that is an entire branching factor. 2 times the length of the string repetitions of that process, that is exponential. The number of productions in the grammar raised to 2 times the length of the string is the worst case for the number of derivations that we end up needing to parse. So it's exponential growth based on the variable that is the length of the string. And if you have a large string, like the number of characters or tokens in a program that you write, can we answer a question like, is this program in this language, very easily? And the answer is no. Exponential growth grows way too quickly. For those of you who have taken my classes, I've probably tried to do this before, but does anyone know or remember the concept of, we take a single piece of paper You fold it in half, then you fold it in half, then you fold it in half, then you fold it in half. Eventually, this becomes completely infeasible, but how many repetitions of something that is this thin does it take in order to span the length of the observable universe?
So isn't it 64 degrees from here to 42?
Yeah, it's in the 40s from here to the moon, and it's in the 60s from here for the observable universe.
What?
Yes, folding a single piece of paper 60-something times gets you the entire diameter of the observable universe.
Doubling its height every time.
Yes. That is how powerful exponential growth is, which is phenomenal if that's a good thing. If you take the inverse of exponential, you get logarithmic. And that tells you if you can log a log 60-something times, then you could the number of pieces of paper that would span the observable universe, you could solve that. If you took the log of the log of the log of the log 60-something times, you could solve that in one statement. So logarithm, inverse exponential, immense power. Exponential, so disgusting that even a 60-something statement, it would take a number of CPU cycles equal to the number of sheets of paper to span the observable universe in terms of cycles in order to answer that problem of just 60-something statements in a program. So we cannot have anything exponential within a 10-foot pole, within an observable universe pole of the programs that of how we're going to build a compiler to parse this. So exponential is just off the table. So this is a great intuitive idea, but unfortunately, it just cannot be used. We need something that is more efficient than that. So a cubic method exists. At the moment, I'm saying they are complicated. We are going to come back to this, explore this cubic method, and it will be the first thing that you program.
They're complicated, don't do it.
Not yet. We'll come back to that complication and I'll take a couple of classes to really draw it out on the board to make sure that the concept of exactly what you have to do is clear. But to get that cubic method, the grammar has to be in a particular form that I haven't introduced yet. So we're going to return to it after we've discussed it. The second thing you're going to program is a linear time method for special cases. So we can actually parse things in linear time if this grammar is an LL1 grammar. We'll talk about what an LL1 grammar is very late in this class, probably week 9, week 10, and that'll be the last thing you implement in terms of code. But it's really cool to see it work because going from exponential to linear is an incredible speed up. Let's start talking about different grammar types. So let's first talk about the concept of a simple grammar. So in order for a grammar to be a simple grammar, we need to have productions in a particular form. Very much like a regular grammar restricted it to be in a particular form, in order for a grammar to be simple, it needs to have all of its productions in the form of a non-terminal followed by some sequence of terminals, followed by 0 or more non-terminals. This was not allowed in regular grammars. We had to have some number of terminals followed by a single non-terminal, but now we're stating we can have an arbitrary number of non-terminals in a single production as long as they all show up at the end. On the other hand, any pair of non-terminal to terminal must appear at most once in the grammar. So let's ask, is this grammar simple? Does this grammar follow those two rules? We have one yes. Anyone else with an opinion? Yes wins the day. It is simple. How about this one?
No,
Why?
because it has 2 pairs of non-terminals within the grammar.
Yeah, non-terminal to terminal appears at most once in the grammar, so this is not. We can produce S arrow A something and S arrow A something. We cannot have that branching factor. So it's production 1 and production 3 that break this from being a simple grammar. What's nice about simple grammars is there are quite a few features that we can use and we can model via grammars of this type. So it's an important grammar type to know to be able to represent those concepts. But it's not as frequently used in outside theory. This is because it can actually be parsed very similarly and linearly, very much like regular grammars can be. It's a little bit more complicated, but we can still parse them without anything fancy in polynomial time. We hinted at this, but now we need to go into it in more detail. The concept of ambiguity of grammars. We said we'd come back and say why this is terrible. We'll define ambiguity. It's ambiguous if there is some string in the language that can have multiple different parse trees constructed that derive that same string. So as an example, we'll take our old friend, the curly brace / parentheses grammar. And we want to figure out if we can have an open, open, close, close via multiple different parse trees. Ambiguity, I don't think that it's great that it exists in spoken language, but in programming languages, we cannot have it. We cannot have a statement mean two different logical truths. There must be a one-to-one mapping between a statement and what it means, the logic that it means. And maybe you can have multiple different statements that mean the same logical construct, but you cannot have one statement that means multiple different constructs. So many to one is okay, one to one is okay, one to many cannot happen. Otherwise, you type some statement, how is the compiler supposed to know what you mean? If it could mean two different things, suddenly we need non-determinism. There's going to be multiple different outputs to your program, only one of which is the one you intended. How does that work? It doesn't. So we can always rewrite ambiguous grammars to remove the ambiguity, and I'll show you how to do that. So first, we can just visualize why this is ambiguous. These are two different parse trees that generate that string AABB. Does everyone see how both of these parse trees generate AABB and how they're very different parse trees? Let's talk in more detail. We know that grammars can express mathematical expressions, right? We've seen how we could start to model parentheses, but let's actually dive into a grammar that actually represents mathematical computation. This is a simplified grammar for mathematics that allows for parentheses, multiplication, and addition. Take a couple minutes. In fact, maybe you even want to take the rest of the class. Work through this grammar in your mind and try to come up with why does this allow for order of operations? Why does this allow for something that allows you to put parentheses around and change up the order of operations? So we're restricting variables to A, B, and C just for simplicity. We want to be able to generate the quantity A plus A times whatever, doesn't matter what we generate, but any legal mathematical expression using addition and multiplication using A and B and C. I said this allows for addition, multiplication, and parentheses, but I never stated that it used an order of operations that expresses our typical order of operations. Does this do that, or does it reverse it? What gets natural precedence? Is it addition or multiplication? Draw out some examples and see if you can come up with the order of operations that this grammar generates. Anyone have any thoughts or insights? What do we think the order of operations is? Yeah,
Does this get, the order operations like addition and multiplication are the same like priority?
yeah. It's undefined, or there is no order of operations to this. You're basically gonna do the operations left to right regardless of parentheses. We don't
You have
really
to do
state that parentheses change the order of operations.
Symbols.
Yeah, they're just symbols with the same precedence. So this is one reason why grammar ambiguity is bad. Because now you have a statement in front of you, and we don't have one way to come up with an answer to that mathematical expression. Depending on how you change the precedence of that, you will come up with different answers. And it does not represent a particular order of operations such that there is one answer to any particular problem because we don't define it. That's a really big problem if you're trying to represent mathematical computation in a programming language and you're trying to generate a grammar that does that. So we need some way to actually embed order of operations into our grammar such that we're going to evaluate multiplication before we evaluate addition. Unless there are parentheses that tell us to override that. Any ideas about how you could modify this grammar to embed order of operations inside of it? Yeah,
Build a classic computer science solution, just add memory to it. Add more memory.
we can make changes to this in a way that perfectly maps to and customizes the order of operations to whatever we want. As computer scientists, we have unlimited power. We have to keep ourselves from becoming Palpatine. But we can if we want to. Just change up the order of operations because you want to. Make a programming language that's just a meme programming language that whenever you launch an application, randomizes the order of operations of all mathematical. Who knows? Why not? The chaotic evil in me says that would be a great idea.
Build a system that changes which compiler you're using.
Yes.
Run.
So I'm gonna leave us hanging on this because we're right at the end of time. And this will be a mystery with a plot twist that we will come back to on Monday because we are reviewing tomorrow and taking an exam on Friday. But we will come back to this later. I have office hours starting now. If you have homework related questions, exam related questions, why did I take this class related questions? Let me know. I'll do my best to answer them.
So I thought they had.